Okay, welcome back everyone, and we're talking about moment of inertia today. And now in class and in previous lectures we've started establishing a duality between linear quantities such as position, displacement, and those would correspond to angular position, angular displacement, velocity, angular velocity, and so forth. Now, time is of course universal and throughout the duality, and we had acceleration and angular acceleration as well. So what we haven't talked about is the question here, what about mass? And where does mass fit in with this duality here? So to do that, let's first talk about inertia first. And so here's a scenario. We have a stoplight, and at that stoplight we have a Porsche versus a semi-truck. And so who's going to win, the truck or the Porsche, when in other words, when the light turns green, who's going to take off first, the fastest, and move quicker through the stoplight? And of course, we know the Porsche is going to do that. And why? Assuming they both had exactly the same amount of power or engines, the Porsche would win the race because it has less inertia. And so that gives us an idea of what we mean by inertia. It has something to do with the mass, and in particular, inertia is the property of mass to resist change in its state of motion. And so the more mass an object has, the more inertia it'll exhibit. And so that's why the Porsche always wins in this scenario. And you could extrapolate this to other physical analogies. So with that in mind, what we want to do here is take a look at a DVD disc or a CD disc or some I know those are becoming old media, or say a Blu-ray disc that's rotating. So we have rotation of a disc. And now if you imagine this disc sitting inside a Blu-ray player or some kind of media player, it's going to be rotating. So things are moving, which means intuitively that there should be some amount of kinetic energy associated with it. However, it's not moving distance-wise. It's not leaving the room, and it's not moving its specific point. This point right here is remaining fixed. So you got to ask, well, 1/2 mv squared is usually how we deal with kinetic energy. 1/2 mv squared, but it's not moving. It is rotating, but it's not moving linearly. So there has to be some kind of new form of kinetic energy that we haven't dealt with, and that new form of kinetic energy is what we call the rotational kinetic energy. So look back at our example. Here we have two pieces of mass, really tiny parts of the Blu-ray or DVD disc here. And of course they're at some radius r1 and radius r2, and they're moving or rotating. And so if they're rotating, they're going to have some tangential velocity here, and then right here they'll have again tangential velocity. So when the object gets to here, again it'll have some tangential velocity there. Here again there'll be some tangential velocity component, and so forth throughout the rotational motion of M2 and M1 as well. And so we can now write these components down. V1, which is going to be the relationship between linear velocity and omega, which we've already established is just multiplying omega by the radius. So V1 should be R1 omega. And keep in mind that the omega is the same for the entire disk. Doesn't matter where you are from the origin all the way out to here. It doesn't matter because the DVD or the Blu-ray is always going to rotate at the same omega, irrespective of particle. So you have V2 equals R2 omega. And so now we can ask, well, what are the kinetic energies of each of these masses? So K1 be M1 V1 squared over 2, but then we will use then we will use this relationship here and to simplify the expression to m1r1 squared omega squared. And so now we do the same thing for K2 and we get it in terms of omega and r. Now keep in mind, remember, omega is the same. And we could pick equal masses, and of course the 1/2 is the same. So the only thing that differentiates these two right here are R1 and R2. And so if you look over here, R1 is smaller than R2, so obviously K2 must be bigger than K1. Okay, so based on the radii. And now I could ask the same question. Well, what if I picked a mass here, a mass here, a mass here, a little piece of mass here, and so you see the whole disk is comprised of little pieces of mass. So what we should do then is actually to find the total. To find the total is to sum over all complete masses. And so if you look at this, we have 1/2 some object here times a velocity squared. Okay, so that makes this part here look like a mass, right? It would be 1/2 m omega squared, and this piece here is what we actually call I, or the rotational inertia. So I is a rotational inertia, or rotational mass. So I is the rotational mass of the entire DVD-ROM or Blu-ray disc as it's rotating. So this gives us two new things we have to consider here. We have K, the kinetic energy of rotation, which is 1/2 I omega squared now, and then I, which is the rotational inertia as a sum of all pieces of mass times the radii squared. Okay, and why is this important? What does this seem to matter at all? And it does matter because what we've done in the past is we've considered an object. We've considered an object, say like a crate, and it's starting from rest here, v naught equals 0, but it's starting at some height h here, and then there's no friction. So there's no friction, and then it starts sliding down the incline, and as it reaches the bottom here, it has some v, which we don't know, but we could calculate this v because we know E initial equals mgh, E final equals 1/2 mv squared. These have to be equal. Mgh equals 1/2 mgh v squared. This cancels and we get v equals 2gh the square rooted. So we see that up here we started with purely gravitational potential energy, which was converted on its way down, converted down here to purely kinetic energy. But now I could get rid of this crate, and I could replace the crate with, say, a hoop. And so now the hoop is going to roll down, and you have to ask the question, well, I know how much energy I need, gravitational energy is going to start here and be converted down here to kinetic energy. But how much energy of that gravitational potential energy do I require to actually make the object rotate, right? Because it's going to roll, right? It's going to roll down the incline. And so I have to actually make it rotate. And that depends on the actual geometry. Okay, so This I, which is rotational inertia, is a mass's property to resist change in its state of rotational motion. So if an object is not rotating and you want to make it rotate, you have to overcome its rotational inertia. So let's take a look at that. Here we have a small demo video. And you can't hear this person, which is fine because I have the sound muted. But basically what this person is going to do is he has a solid disc and a hoop. And the person is going to want, that's a side demo he does, we don't need to worry about that. He's going to ask a question about, we're going to race the hoop versus the solid disc down the incline. And so he's got the hoop set up and the solid disc set up. He's going to remove the 2x4, and then they're going to begin to roll purely based on the gravitational force pulling them down the incline. And the question is, which hoop wins the race? Which hoop or disc, which object makes it down to the bottom first? And you can think about it. So if you think about it, pause the video and try to get an idea which one would be harder to begin to rotate, to overcome its rotational inertia. And so let's go ahead and continue the race. And you see the solid disc makes it down the incline first. And that's because the solid disc has less rotational inertia. So it's going to be easier to bring the solid disc into rotational motion compared to the hoop. Okay. So, and this is why we had this formula here for rotational inertia, but it's really hard to sum up every little piece of mass, especially in algebra-based physics. If you have calculus under your belt, it gets a little bit easier, but it's still complicated. So we'll actually refer to the tables in the books on the value of rotational inertia for each object. So here you see you have the hoop, and the hoop is just mr squared. So it's the mass of the hoop times the radius squared. Whereas here you see the solid cylinder, the solid disc is 1/2 the rotational inertia of the hoop. That's why the solid disc won. It has 1/2 the amount of rotational inertia per same amount of mass as the hoop. And we have other geometries. This one is important. This is like a door. And we'll talk about spheres. So here's a hollow sphere, a solid sphere. And now we can move on to start solving some problems. But before that, we have to redefine our idea of total kinetic energy, which will now include linear kinetic energy, which is 1/2 mv squared, and rotational kinetic energy, which is 1/2 I omega squared. And written out here. So the total mechanical energy includes potential energy, linear kinetic energy, and rotational kinetic energy now as well. So we can address a question here. So let's just look at the question and the scenario. A solid ball is released from rest at the top of an incline of height h. What's its speed at the bottom? Okay, so we're releasing this at rest. It reaches the bottom, and we want to know what the velocity is as it reaches here. We're dropping it from height h. Now, if this was a crate on a frictionless plane, we know v would equal square root of 2gh. We just figured that out above. So let's look at here. So here we're going to set our initial here, which is mgh, and then our final E final down here, which will be 1 half mv squared plus 1 half I omega squared. And I gave you, this is a solid ball, so we have 2/5 mr squared is I. So let's keep that up here. So I will be 2/5 mr squared. So that means EI equals EF, so mgh equals 1 half mv squared plus 1 half I omega squared. So mgh, and then we have 2/5 mr squared, and omega, remember, is, well, omega I know v equals r omega, so omega equals v over r, so I get v over r squared. And so I get mgh equals 1 half mv squared plus I can cancel these two, so I get 1/5 m, and then this r cancels with this r squared, so I get mv squared here. And now I get mv squared 1 half plus 1/5, so I get and then this is mgh here, so the m's cancel, so we get gh equals, and then the common denominator will be a 10, so I'll get 5 over 10 plus 2 over 10, so we get v squared equals 10gh over 7, so v equals 10/7 gh square rooted. So now you can compare your result, and 10/7 is less than 2 gh. So you see that there was a certain amount of energy, gravitational energy, that was converted to rotational, to the fact that we needed to overcome the moment of inertia here. And so we here. Now let's look at the example from the video. Okay, let's figure this out. A solid cylinder and a ring of equal mass and radius are raced down an incline of height h. What are the respective velocities, and subsequently which one reaches the bottom first? So whoever has the higher velocity at the bottom of the incline obviously will be declared the winner and made it down the incline quicker than the other. So let's take a look here. So again, we're doing the same scenario here. And so we're going to drop either the solid ring or the solid or the hoop from height h here, and then down here we want to know what is v going to be. So we'll have our initial energy state here and our final energy state there. So E initial is mgh, E final 1 half mv squared plus 1 half I omega squared. So we get mgh equals 1 half mv squared plus 1 half I omega squared. And we can keep working on this, so we'll get 1 half mv squared plus 1 half I, and then this will be v squared over r squared. And now I just got to figure out my I. So for the hoop, it's mr squared. So let's look at the hoop, or the hollow cylinder. We'll have mgh equals 1 half mv squared plus 1 half mr squared v squared over r squared. So my r's cancel, and I get mgh, and then a half plus a half is 1, so I get mv squared. The m's cancel, and I get v equals square root of gh. Okay. Compare this to 2gh if it was a crate on a frictionless plane. We've lost half the amount of velocity for the fact that we needed to bring the hoop into a rotational state of motion. Okay, so now we do for the solid cylinder, which is 1/2 mr squared, we get mgh equals 1/2 mv squared plus 1/2 times a half mr squared v squared over r squared. So my r's cancel, my m's cancel, g h equals v squared 1/2 plus 1/4, and so we get gh equals v squared and then 3/4. So we get v equals 4/3 gh square rooted. And so we get 4/3, which is 1.333 gh square rooted versus 1 gh. So this is obviously a higher speed than this, so that means that the solid disk makes it down the incline first and has a higher speed at the bottom. Yes. Okay, so that concludes our introduction to moment of inertia, or rotational inertia, or rotational mass, and we'll continue this discussion in subsequent videos and in class.